Hi everyone, thank you so much for clicking onto the video. Now we're going to look at some harder questions for redox titrations. So in this question, a sample of solid ethane dioic acid has been contaminated with potassium ethane dioate. A 1.780 gram sample of this mixture was made up to a 250 centimeters cubed solution with distilled water in a volumetric flask. A 25 centimeters cubed sample was titrated against 0.100 moles per decimeters cubed of sodium hydroxide, requiring 17.35 centimeters cubed. Another 25 centimeters cubed sample was acidified with sulfuric acid and titrated against 0.02 moles per decimeters cubed of potassium manganate solution, requiring 24.85 centimeters cubed. Calculate X. So first, I'm just going to draw a quick diagram to try and get my head around what's actually happening, because these questions can be really long. So you can sometimes mix up all the numbers for different solutions. So I always like to draw a diagram first. So we've got 1.780 grams at the beginning. And I just put this into a box. And in here we've got the ethane dioic acid. And we've also got the potassium ethane dioate. And then this is made up to a 250 centimeters cubed solution using distilled water. So we still have the same amounts of the ethane dioic acid and potassium ethane dioate, because we haven't changed that, we've just added water to it. And then we take a 25 centimeters cubed sample and we titrate it with some sodium hydroxide. So we used 17.35 centimeters cubed, and the concentration was 0.100. And then we took another sample, another 25 centimeters cubed sample, and we titrated this with potassium manganate, and we used 24.85 centimeters cubed, and the concentration, was 0.02. So now what we're going to do first is we can either work out the number of moles of sodium hydroxide used to titrate the 25 centimeters cubed sample of the solution, or we can work out the number of moles of potassium manganate. So I'm just going to use the sodium hydroxide to start. So the moles of sodium hydroxide used is equal to concentration times by volume. So we've got 0.100 multiplied by 17.35, and it has to be converted to decimeters cubed, so we need to divide it by 1,000. And this equals 1.735 times 10 to the minus 3 moles. And now we think about what this actually reacts with. So in the 25 centimeters cubed sample, we've got some ethane dioic acid and also some potassium ethane dioate. And so because sodium hydroxide is a base, that means it reacts with acids. And because the ethane dioic acid is the only thing in there that has H pluses, that means that is the only thing that reacts with this sodium hydroxide. The sodium hydroxide actually doesn't react with the potassium ethane dioate because it doesn't have any H pluses. And so this is what reacts with the sodium hydroxide. And now we have to work out what ratio they react in. So the sodium hydroxide dissociates to give one OH minus ion, and this ethane dioic acid dissociates to give two H plus ions. And so that means that the reaction ratio is 1 to 2. So for every ethane dioic acid we have, we need to react it with 2 sodium hydroxides. And so the moles of the ethane dioic acid we have will be half the number of moles of sodium hydroxide that we used. And so we get that the moles of ethane dioic acid is equal to 1.735 times 10 to the power of minus 3 over 2, which is equal to 8.675 times 10 to the minus 4 moles. And now there's something really, really important that we need to remember, and that's that this is just in 25 centimeters cubed, because we only titrated 25 centimeters cubed. So this is something really key that we need to remember. And this means that to find the number of moles of ethane dioic acid in the 250 centimeters cubed, we need to multiply this number by 10. So therefore, in 250 centimeters cubed, the moles is equal to 8.675 times 10 to the minus 4 times by 10, which is 8.675 times 10 to the minus 3 moles. And now we can work with the potassium manganate. So we have to think about, first of all, we need to work out the moles of it. So we can quickly do that. So we've got 24.85 centimeters cubed. So the moles of manganate. So the moles of manganate will be equal to the moles of potassium manganate we have, because it's a 1-to-1 ratio. So for every potassium manganate we have one manganate ion. And so the moles of manganate will be equal to the moles of potassium manganate, which is equal to the concentration of potassium manganate multiplied by the volume of potassium manganate. So we have 0.0200 multiplied by 24.85. And we need to convert this to decimeters cubed again, so divide it by 1,000. And this gives us 4.97 times 10 to the minus 4 moles. And again, now we need to think about what this actually reacts with. So if we think back to redox titrations, we know that the manganate ion can oxidize the ethane dioate ions. And so the equation that we need is between manganate and ethane dioates, because in the 250 centimeters cubed solution, we have ethane dioate ions. So that means that they will react with the manganate. And so that's the equation that we need to form. I'm just going to write down the full equation, but if you can't remember it, or if you haven't remembered it, then of course you can write the half equations and then just construct it into the overall equation. So the overall equation is that we have 2 manganates reacting with 5 of these ethane dioates and 16 H pluses. And this is to form 2 Mn2 plus ions and 8 waters and also 10 carbon dioxides. And so now we can find the moles of this ethane dioate ion that we've used in the titration, because from the equation we can see it's a 2-to-5 ratio, and so we can use the moles of manganate to help us work it out. So the moles of ethane dioate ions that we've used is equal to 5/2 multiplied by the moles of manganate, so 4.97 times 10 to the minus 4, and this is equal to 1.2425 times 10 to the minus 3. And now again we need to remember that this is only in 25 centimeters cubed, because that's all we titrated it with. And so this is in 25 centimeters cubed. And so that means that in 250 centimeters cubed, the moles is equal to 1.2425 times 10 to the minus 3 multiplied by 10. And so this gives us 0.012425 moles. And again, now we need to think about what this manganate actually reacts with. So we know that manganate reacts with ethane diarrhea. And that means that it's reacted with both the potassium ethane diarrhea and also the ethane diaric acid, because we have ethane diarrhea here and also ethane diarrhea here. So these have both reacted with this potassium manganate, because the manganate ions have oxidized these ethane diarrhea ions. And so in order to work out the amount of moles of potassium ethane diarrhea we have, we need to take away the moles that we worked out earlier of the ethane diaric acid from the total moles of C2O42 minus ions we have in the 250 centimeters cubed. And so what we do is the moles of this potassium ethane diarrhea is equal to the moles of C2O42 minus in the 250 centimeters cubed, because this includes both potassium ethane diarrhea and ethane diaric acid, because they both have C2O42 minus ions. And we have to minus the moles of the ethane diaric acid that we found before. And that's why we needed that sodium hydroxide, because it only reacted with the ethane diaric acid. So now we can use it to find the moles of potassium ethane diarrhea. And so we get 0.012425, and then before the moles of ethane diaric acid, we got 8.675 times 10 to the minus 3. So this gives us 3.75 times 10 to the minus 3 moles. And now the next thing we want to do is to find the MR of this potassium ethane diarrhea. And in order to find MR, because we've already got the moles, we need to find the mass. And so the way we find the mass is if we find the mass of ethane diaric acid and take that away from the original mass that was given in the question, then we should be able to find the mass of the potassium ethane diarrhea. So we know the moles of this ethane diaric acid. So we have that the moles of ethane diaric acid is 8.675 times 10 to the minus 3. And we could work out the MR of this ethane diaric acid as well. And so then we can work out its mass. So MR is equal to 2 plus 12 times 2, which is 24, plus 64, plus 2 times H2O, and 1 H2O is 18, so 2 times H2O is 36. And so this gives us 126. And so we have the equation that moles equals mass over the MR. And so rearranging, we have that mass is equal to moles times by the MR. And so the mass of ethane diaric acid is equal to 8.675 times 10 to the minus 3 multiplied by 126. And this gives us 1.09305 grams. And now we can find out the mass of potassium ethane diarrhea, because we're given the mass of the total sample in the beginning. So here, the 1.780 grams is the mass of the whole mixture of the potassium ethane diarrhea and and the ethane dioic acid. And so we can just take it away. So we have that the mass of potassium ethane dioate equals the mass of the mixture minus the mass of ethane dioic acid, and that equals 1.780 minus 1.09305, and this gives us 0.687 grams. So now we can work out the MR because we've got the mass and we've also got the moles. So the next step is looking at the MR. So again, we have the equation moles equals mass over MR. That means that MR is equal to mass over moles. So it equals 0.687 over the moles of potassium ethane dioate that we have, which we worked out to be 3.75 times 10 to the minus 3. And this equals 183.2. So this is for that potassium ethane dioate. And now we can take away the MR of this K2C2O4 bit. So the MR of XH2O is equal to 183.2 minus the MR of K2C2O4, which is equal to 39.1 plus another 39.1 plus 24 plus 64, and this equals 17. So now we can find X by dividing this by the MR of H2O. So X equals 17 over the MR of H2O. And this is 17 over 18. So this gives us 0.9. And so we round it up, and therefore X is equal to 1. So before I move on to the second question, feel free to click off the video and try it for yourself first. So a piece of rusted iron was analysed to find out how much of the iron had been oxidised to rust. So the rust is hydrated iron 3 oxide. A small sample of the iron was dissolved in excess dilute sulfuric acid to give 250 centimetres cubed of solution in a volumetric flask. The solution contains Fe2 plus ions from the unrusted iron dissolving in the acid and Fe3 plus ions from the rusted iron. For A, 25 centimetres cubed of this solution requires 16.9 centimetres cubed of 0.02 moles per decimeters cubed of potassium manganate for complete oxidation of the Fe2 plus ions. Calculate the moles of Fe2 plus ions in the sample titrated. So what we do is we think about how manganate reacts with Fe2 plus ions. So manganate ions oxidize Fe2 plus ions to Fe3 plus ions. And so these are the equations that we need to use in order to get the overall equation. So again, I'm just going to write the full equation, but if you hadn't remembered it, then of course you can write the half equations and put them both together. So we have 5 Fe2 plus ions reacting with a manganate ion, and also 8 H pluses, and this forms 1 Mn2 plus ion plus 5 Fe3 plus ions plus 4 waters. And so now we work out the moles of manganate that we used, and then we can use the ratio to work out the moles of Fe2 plus that we used. So the moles of MnO4 minus is equal to concentration times by volume. So we have concentration of 0.0200 and multiplied by 16.9 times 10 to the minus 3. And this equals 3.38 times 10 to the minus 4 moles. And now we use the ratio to find out how much Fe2 plus we have in this sample. So we see that it's a 1 to 5 ratio. So for every manganate, we have 5 Fe2 pluses. So that means that the moles of Fe2 plus is equal to this 3.38 times 10 to the minus 4 multiplied by 5. And this gives us 1.69 times 10 to the minus 3 moles. For B, to a second 25 centimeters cubed of the rusted iron solution, an oxidizing agent was added to convert all the Fe2 plus ions present to Fe3 plus ions. The Fe3 plus ions were titrated with a solution of EDTA 4 minus ions, and 17.6 centimeters cubed of 0.10 moles per decimeters cubed of EDTA were required. Assuming 1 mole of EDTA reacts with 1 mole of Fe3 plus ions, calculate the moles of Fe3 plus ions in the sample. So we do a similar thing, but this time with EDTA instead of manganate and Fe3 plus instead of Fe2 plus. So we don't have to write out the equation because we don't know it. We're told that it's a 1-to-1 ratio. And so we work out the moles that we have of EDTA first. And this is equal to concentration times by volume again. So we have 0.10 multiplied by 17.6 times 10 to the minus 3. And this gives us 1.76 times 10 to the minus 3 moles. And now we can work out the moles of Fe3 plus, because it's a 1-to-1 ratio, so it's just the same. So 1.76 times 10 to the minus 3 moles. And then for C, from your calculations in A and B, calculate the ratio of rusted iron to unrusted iron, and hence the percentage of iron that had rusted. So now what we have to think about is how we work out the amount of rusted iron that we have. So we have Fe2 plus, which gets oxidized by manganate ions to form Fe3 plus. This is the first sample. And in the second sample, we have a mixture of Fe2 plus and Fe3 pluses. And so when we added an oxidizing agent, it converted everything to Fe3 pluses. And then we used EDTA 4 minus to titrate the Fe3 pluses to find out how much Fe3 plus we had. And so this means that the amount of rusted iron is equal to 1.76 times 10 to the minus 3, which was basically the total. So this 1.76 times 10 to the minus 3 was actually in the mixture how much Fe3 plus and Fe2 plus we had, because we converted it all to Fe3 plus before we added the EDTA, and then minus the moles of Fe2 plus that we found by adding the manganate. So 1.69 times 10 to the minus 3. And so this gives us 7 times 10 to the minus 5 moles. And we also know the amount of unrusted iron, because that's just the amount of Fe2 plus ions that we had. So unrusted iron is equal to the 1.69 times 10 to the minus 3 moles. And so now we can work out the ratio. So the percent rusted is equal to the rusted over the unrusted times by 100. And this is equal to 4.1%. And the ratio between rusted and unrusted is 7 times 10 to the minus 5 to 1.69 times 10 to the minus 3. That's the ratio.